Welcome back. Hope you are well. The fundamental theorem of calculus is one of those types of theorems that we use all of the time without even really acknowledging or recognizing its presence. Whenever we are using fundamental theorem of calculus, or whenever usually we integrate a function, we are usually using the facts that for the classes of functions that we're working with, the integral can be thought of as the antiderivative of a function, right? We are using this as a way of kind of doing this. We're not usually deriving these things by the Riemann sum formulas or anything like this. Instead, we are saying what function, if I were to take its derivative, would give me the function that I'm trying to integrate. That would be the integral of this function. But in order for us to be able to understand and show how the fundamental theorem of calculus can actually be proven, we need to make sure that we are very rigorous with how we define the integral, which is exactly what we want to do today. Today, we're going to be discussing a type of integral that we're going to be working with, namely the Riemann integral, which is the same type of integral that is introduced to us when we are usually taking the calculus sequence for the first time. Now, I mention this because there are more and different types of integrals out there and other ways to treat the Riemann integral itself, but we're going to see a treatment of it today in a way that's very similar to how we have seen it in a calculus sequence. So that's going to be our goal for today, is going to be taking a look at the integral. Now, again, when we try and calculate integrals with using this, we are not going to be using the fundamental theorem of calculus, at least not yet. That's going to be something that we talk about in later this week once we have given a more rigorous treatment to what these Riemann integrals are. Now, Riemann integrals, you may remember all of these sum and sum formulas that take place, right? You're summing over, in particular, areas of rectangles whenever you're trying to figure out what an integral is, because the attempt is you're trying to see, is there a good notion of area that this integral can give? The area being the area under the curve, or the area between the curve and the x-axis. And so with this kind of positive and negative polarity, depending on which one is first, the x-axis or the curve, which one is higher than the other. And our way of doing this is to take our beginning and ending points. Say, for example, we want to integrate going from A to B, and making those endpoints of a partition of our interval going from A to B. Now, a partition is just going to be a sequence of points that are in ascending order that start at A and end at B. Right, that's exactly how we're going to define that up here. It is a finite subset of your closed interval. It must include those endpoints so that we know, okay, we're actually finding an area from A to B. Now, what we end up doing with this is that once we have this finite subset, which is given right here, the things that I'm circling in red, what we end up doing after that is we say, okay, I want to, for every sub-interval that I create, that is, every interval that exists between any 2 points of my partition that are right next to each other, then I can pick an arbitrary sample, like a T1, somewhere inside of there. And I can say, okay, I'm going to dictate my height of my rectangle with length going from x0 to x1 in the following way. I am going to make the height of this rectangle equal to the function height at that point. So if this is, for example, y equals f of x right here, then this point right here is f of t1. So the height of this rectangle is f of t1, and the width of this rectangle is just the distance between these 2 points. This is x1 minus x0. So if I were to find the area of this rectangle, it would be height times width, or height times length, and that's going to be f of t1 times x of 1 minus x of 0. Once I've finished with that rectangle, I move on to the next rectangle and do the exact same thing, this time with f of t sub 2. And I add the area that I would get from that to the previous ones, and I continue to do this to all of the other rectangles here in this diagram. Now, this is going to be very much relative to the types of partitions that I choose, as well as the samples that I choose with regards to these partitions. So let's talk a little bit about how this can be done in an arbitrary sense, not just in terms of our picture there. Here, we're going to say x0 to xn, because there could be n plus 1 points in this partition, be the list of all of these elements. Notice that the first element is a and the last element is b. This is going to divide the interval from a to b into the subintervals we were talking about before. Now, we're going to associate to a partition something called the norm of the partition. And what we'll define as the norm is going to be the maximum of all of those lengths of those subintervals. So for example, I might look down here and notice that the largest width between two rectangles is x1 and x2. So with this particular partition, if I use this kind of picture as a guide here, then I would say that this is going to be x2 minus x1, because that's the largest possible length between any two adjacent partition elements inside of my partition. Now, the goal is to make these rectangles as small as possible, because right now you can see that I am doing an okay job of approximating the area underneath the curve here. But I would do a better job if I had, instead of working with 4 rectangles, what if I had worked with 8? What if I had, instead of having all of this extra stuff over here on the left-hand side, what if I had made a little division so that I was looking at this rectangle instead and this rectangle instead? Then you can see, okay, well, now I have cut down on that little bit of excess area that I was working with before. And sometimes what ends up happening is that if you have a nice enough function, you can say that what you get after taking this process of limiting the number of rectangles you have to infinity, that what you end up getting is actually the area underneath the curve in a very rigorous sense. Now, we're not going to talk about this as the number of rectangles going to infinity. I can make infinitely many rectangles in just this region here. So instead, what I'm going to say is I want to take my norm of this partition to go to 0. That's going to be my goal. The largest possible subinterval, I want it to go to be of 0 length. And the way that we're going to discuss how that works and a limit with respect to some of these things is that we're going to call particular partitions, some of them refinements of other partitions. For example, let's say that we're given two partitions P and Q on the same interval. And we're going to say that Q is a refinement of P if Q has more partition points than P does. It includes all of the partition points in particular of P and also some more. In particular, we notice that this is going to imply that the norm of Q is less than or equal to the norm of P. So for example, here would be a partition of this other P, x0 to x4 partition on this picture. That would be a refinement of it. I would take maybe this point right here and this point, and maybe even just include all of the other points. I have to make sure that I am including each and every one of these, and maybe I just call this value B. Then Q, which is just x0, B, x1, x2, x3, x4, is a refinement of P. All I had to do was add 1 point, and suddenly I got a refinement. And in fact, the only thing that determines whether or not you have a refinement of your original partition is if every single element of the original partition is in your refinement, or the thing you're claiming is your refinement. That's all it means to be a subset. In fact, we didn't even need B. Even if you just look at Q being the same partition as P, this is still considered a refinement given our definition. Of course, what we want to do is consider refinements of particular starting point partitions until our norm goes to 0. So we're not really quite interested in making Q just the same as P. We're interested in adding more and more points. So a Riemann sum is going to be with respect to one partition and one sample choice that you make for each subinterval that is given there in that partition. Let's make sure we highlight the important parts that are taking place in this partition, or in this definition. A Riemann sum of a function, so first things first, I choose a function that is the curve that we were looking at in our previous picture, with respect to a partition. So once I have a function, I look to divide the interval going from A to B, that being the domain of this function, the part that I wish to integrate. For this partition, I divide it all the way up so that x0 is A and x of n is B. Then once I have that partition, I'm going to go through and say in each of those subintervals, I'm going to pick a x value that's going to dictate the height of that rectangle once I consider the function value at that point. Then all we do is we say, okay, in order to figure out what this Riemann sum is going to be, I'm going to multiply height times width and then add up all of those heights and widths together. That's going to give me the aggregate sum of all of those rectangles that I have created. This is not necessarily the area of underneath the curve itself. In fact, in this form, it very likely is not, because all we've done is we have created rectangles that approximate the area underneath the curve here. So here we have all of the things that are set forth as before. The norm of P, all of these definitions are all of the same. And we're going to say that the Riemann sums converge to a limit I of f, and this is what we're going to be calling the integral of f. This is hopefully the thing that actually gives us a notion of area underneath the curve. As the norm of the partition, the norm of the partition P goes to 0 if, and here we have our epsilon delta definition again, if for every epsilon greater than 0, there exists a delta greater than 0, such that whenever you have that the norm of P is small enough, then this is an actual limit of this function. In fact, this looks very much like a functional limit. The thing that you are allowing to go to 0, though, is not like x values approaching some other x value. This is saying that the partitions, the largest possible subinterval that you have there, is actually going towards 0. So this is what we're trying to show, and when we're trying to do a convergence, is that the Riemann sum is approaching this limiting value of what we're hoping to call the integral of f. So it is not always the case that every function has this happening. If it is the case that you get this limiting value, then the function f is called integrable on the interval from a to b, and the limit I of f is called the integral of f over the interval from a to b. And we denote it like we are used to denoting it from before, the integral from a to b of f of x dx. Okay, so this is our build up. This is our rigorous notion of what an integral is supposed to look like. Something that's interesting here is that not every function has an integral. Oftentimes when we look at functions that we see in Calculus 1, we often are only presented with examples that do have well-defined integrals. But there are going to be plenty of examples out in the world in which there are not integrals for those functions. Now, we are only going to discuss here, I think in this lecture, only the ones that do have integrals. And we're going to focus on those because that's going to be kind of getting us to our slant, our goal of trying to work toward the fundamental theorem of calculus. For example, the constant function is integrable on any interval a to b, right? Anytime that you're making any partition of the constant function, so here, let's say that this constant is right up here, and then this is going from a to b, and then any partition that you make of this is going to be exactly the same, right? I divide up this into what kind of intervals that I would like it to go. And the height of those rectangles is always dictated by the exact same y value because, well, the y value is always the same throughout this entire function. So regardless of my partition, finding the area underneath the curve here is going to be the same as finding the area underneath each of these rectangles and adding those together. But I can also look at this as one big rectangle. If this is of height c, then this is just going to be a height of c times the width of this interval, which is going to be b minus a, which gives you what this formula is for the integral of the constant function. Now, the step function, that is the one that is 1 if x is greater than 0 and 0 if x is non-positive, is also integrable on the interval from -1 to 1. This is going to mean that, well, for this one, it gets a little bit more complicated because if I'm trying to make partitions for this function here, so here's 0, here's 1, then my partition in the middle here has a choice. All of these others are definitely going to have rectangles that are of height 1, this one right here, and all the ones over here are going to have rectangles that are of height 0. But on the inside here, then I have a choice. I can either say, okay, I'm going to sample a point over here, and so my height of this rectangle in the middle of this partition is going to be 0, or I can choose a sample that's over here, and I can have a height that is of length 1. Now, the deal is that as I take my largest possible interval to go towards 0, that means that this interval here is going to have a length that is bounded by the largest possible subinterval length in that partition. And if that's the case, then really this one partition does not really play much of a role because the highest that this possibly can be is 1, and its width is going to be determined by, well, at least by the norm of the partition P. Well, if the partition P, its norm is going towards 0, then really this interval doesn't make too much of a difference. At the end of the day, it turns out that really what I'm doing is just trying to find the area underneath this part of the rectangle, where here I'm going from 0 to 1. And then from -1 to 0, finding that area is just going to give me 0. So in that case, the area is just going to give me 1 for that integral. Now, one big class that we have discussed already that is going to be integrable is the following. Well, first, let's get to this theorem. If a function f is integrable on the interval from a to b, then it is bounded on a to b. b. Now, this is something that we are kind of saying with this one, because otherwise you could take a look at partitions that potentially really do blow up and make this a little bit tricky to work with. Now, continuity is the proposition that we're working with. Continuity is going to imply integrability here. If a function f is continuous on the interval going from a to b, then f is integrable on a to b. Now, this is, again, the proof of this deals with a kind of a notion that we have only skimmed over briefly, which is the notion of any function that is continuous on a closed and bounded region is uniformly continuous. And hence, it has a very good notion of, like, if your delta window is this wide, then you always fit within this epsilon window, regardless of what x value you're choosing in order to center around for your delta window. And because of this, because of your ability to work with this amount of flexibility there, then you can go through and show that indeed all of your integrals actually are bounding toward zero, or they're bounding toward one value, and that becomes the integral limiting value that you have there. Now, if a function f is integrable on the interval from a to b, then it is also integrable on each subinterval going from c to d to a to b, right? And the idea is that you could just take a look at a partition that comes in and has endpoints at c and d, and, well, you can extend that into a partition of all of a and b. Well, if you do that, then you know that that limit is going to go to zero, so that big integral is going to exist, and hence you can look at just the part of that sum that is going from c to d and see that sum is going to be limiting to an actual value, which you can call the integral for that subinterval. Now, one particular way that this is used is in this theorem. If a function f is integrable on an interval going from a to b, then maybe I have a function that, like the step function there, is a piecewise function. Maybe it's a little bit easier for me to think of this, instead of trying to balance this in a specific way or explain every time why the step function works the way that it does. Maybe it's easier for me to instead say, okay, well, I notice that this is 1 as x is greater than 0, so I could break up this interval going from 0 to 1. In that case, I'm just looking at a constant function on this interval. And then I could do the same thing looking at the interval going from -1 to 0. That is also a constant function. So I could really just use this first bullet point twice to find what the integral is for this step function. And that's exactly what this theorem is talking about. Oftentimes you want to, with these piecewise functions, break apart the areas for these functions so that it makes nicer and easier arguments for you to show what that integral is going to be. And that's exactly what we have here. If we have a function that we can split apart for any value c inside of the open interval going from a to b, we can split apart the integral into two. One integral going from a to c, one integral going from c to b. But of course, we have to use our rigorous ideas, our rigorous definitions in order to try and get us to this point. So let's see how we could try and do this. First, since f is integrable on the interval from a to b, we know it is also integrable. That is, it has limiting values on a to c as well as c to b. That was our previous theorem from before. So let's let P be a partition of a to c, and let's pick some samples for that partition. Then let's do the same thing for Q being a partition from C to B and giving us some other various samples for that partition. Then what the connection here to see that these two things are actually going to be equal to each other, not only that these things are all integrable so that these limits exist, but that the sum of the two things on the right-hand side equals the integral on the left, is that we're going to have a key idea. And that idea is going to be that if you take those two partitions, P and Q, and you union them together, right? Because this P right here is A is less than X1 is less than ... is less than B, whereas Q is B is less than, Y sub 1 less than ... is less than C. If you union those together, what you get is another partition of the interval going from A to B. Oops, excuse me, this should, just changing the letters here, I realized that this should be C in the middle, not B. So let me go ahead and change that. So there we go. We've got our partition now for something that is of the entire interval going from A to B with the samples to go along with it. Notice that these samples correspond exactly to the samples that we had for each of these individual integrals, which is going to be key for helping us see that these two things should actually equal the same thing. So our key observation, the thing that we notice, is that whenever you're taking these sums, you can just break apart a sum based off of the fact that you can break it off at that value c, and make that a separate sum. And then add to that the sum going from starting at c and going all the way to b for that definition of the Riemann sum. It's always okay for us to break up a finite sum into two smaller sums if that would suit our fancy. And that's exactly what we have right here. Well, if the norm of P goes to 0, as does the norm of Q, then we can note that the norm of P union Q is actually the maximum of the norm of P and Q. So if they're both going towards 0, the norm of P and union Q is also going towards 0. So that is what we get there. So that means that all of these limits existing, we're just basically taking a limit of this equal to a limit of this. And thanks to the fact that limits of sums work nicely, we get exactly what we would like. We get this formula up here at the top. So this tells us that we can now integrate things like step functions and other sorts of piecewise functions by just integrating each part and then adding them all together. Now, we could also take, instead of looking at just one function, we could integrate the sum of two functions. And the way that that works is also very nice. And that's due, in fact, in part by the fact that the way that the Riemann sum works is linear with respect to its functions. And we'll talk about that a little bit more once we get to the proof of that. But it's the same reason that the scalar multiple works the same way. The alpha can come out. By the way, these two things together tell us that the integral is a linear operator on the space of integrable functions, right? It has the ability to say, okay, f plus g, you can break it apart and make an integral of one plus the integral of the other, and you can bring scalars outside of the linear operator. So that is what we're kind of showing with these two theorems here. So here you have a linear operation to be working with. So let's see what that proof kind of looks like. First, we got to denote our integrals for f and g to be I of f and I of g respectively. And the key observation is that Riemann sums themselves, not even just looking at the integral, but sums themselves are going to depend linearly on the function. Namely, if I were to try and formulate what this function is, f plus g, remember that the way that we define something like this is going to be something like the sum of f of t sub I plus g of t sub I all times x sub I minus x sub I minus 1, where that sum goes from 1 to n, something like this. Well, then notice that I can break that sum apart by just kind of doing a little bit of distribution here. By f of t sub I times x sub I minus x sub I minus 1, notice that once broken apart, is just this. It's the Riemann sum for f with respect to that exact same sample and that exact same partition. The same thing is true when you can check this yourself for scalar multiples for any partition and for any choice of samples that you choose. So for the rest of this, we just need to show that indeed the Riemann sum of f plus g converges to I of f plus I of g. So we're going to show that the absolute value of the difference between the two of them is going to go towards 0. To do this, we'll do a quick triangle inequality for the sum formula, and we'll do a quick fact that the norm is kind of be like kind of multiplicative in a sense. You can bring the alpha out as long as you bring it with an absolute value. And if you do this, then you notice that, well, if these things, if the integral of f or the Riemann sums of f are indeed approaching the integral of f, and the Riemann sum of g is indeed approaching I of g, then these things are going towards 0. In that case, we're pretty good to go. So these Riemann sums are going to go, and so hence S of f plus g, with respect to this partition and sample, will be getting arbitrarily close to I of f plus I of g. Same thing for working with the multiple of that function. So this gives us exactly what we're looking for by the definition of what it means to converge to the limit, with this being this integral here. So we are very much using the fact that the integral is the limit of these Riemann sums. We're using the fact that essentially the right-hand side of each of these things are going to go towards 0 or eventually be less than epsilon for any epsilon greater than 0 that you choose, if you choose a partition with norm small enough. Now, let's kind of keep going here and see a little bit more about what we can do with integrable functions. We're kind of going through now and checking off all of the integral laws and theorems that we are very used to using whenever we construct these integrals. One is that if a function f is integrable on some interval, and you take a look at another function such that the range of the first function, f, is contained within the domain of this second function, g, then the composition g of f is also going to be integrable. A nice little corollary of that is that f and g are going to, if they're both integrable, then so is the product of those two things. So we could see kind of how this works. One thing is that, well, for example, I might be trying to take a look at this if f and f are just like maybe these are the same function for a little bit. Then the composition that's going on here is that one, f is integrable, but I'm also going to be composing this with the function that squares whatever comes into it, right? So maybe I can write it like this. This is g of f where g of x is x squared. In that case, g of f is just going to be f squared, which is f times g in this particular example. We want to just generalize this to work for any f and g, though. So we're going to use a couple of interesting connections with each of these things to try and make this work. Well, the way that we're going to do that is notice that f and g is present somewhere in this equation, which is the expansion of f plus g quantity squared. But notice that if I subtract away f squared and g squared, then what am I left with? On the left-hand side, now I just have a bunch of things that look a little bit like f squared. Maybe I changed the label on each of those. I have f squared on the left-hand side, g squared, didn't matter the letter that I choose, f plus g, that's also fine since we know from a previous theorem that if f and g are integrable, so is f plus g. And the rest of the theorem is essentially going off and doing that very same thing. The fact that fg is now equal to 1/2 of f plus g quantity squared minus 1/2 f squared minus 1/2 g squared means that this is integrable if and only if this is going to be integrable. Well, the right-hand side is definitely integrable because of our theorem from above, because we can just compose the function x squared with the function f. Since x squared is integrable and f is integrable, we then therefore have that f times g is going to be integrable. One more thing that's very useful for us is that sometimes, despite having all of these laws, it is very hard to figure out what the integral of something actually is. Oftentimes, we might see this with examples like sine of x over x, which is a very popular function known as the sinc function. And I can ask questions like, okay, well, what's the integral of this one going from 0 to infinity? And a lot of our basic tools for this one end up failing. But maybe we could get some bounds, some appropriate bounds for this integral instead. Maybe we can use those tools to show that this actually does converge to something. And indeed, that is something that is very well possible. But in order to do that, we need to build up some things like comparison theorems for these integrals. So let's say that f is less than or equal to g for any two integrable functions on the same domain. Then in that case, the integral of f going from a to b is less than or equal to the integral of g going from a to b. And the reason for this is that when you go back to the definition, go back to looking at the Riemann sums, well, if f is less than or equal to g, then there's no way for you to find a way for the Riemann sum of f to surpass the Riemann sum of g in its magnitude, in how large it can grow. And that's because, well, you're looking at the height with respect to the same samples whenever you're looking at this comparison. It's the same partition and the same samples. It's okay for us to do this because we're just going to be taking the norm of this partition as it goes towards 0. And in that case, it is always the case that f of t sub j is less than or equal to g of t sub j. But that's exactly the thing that's different in those two integrals. So because this works neatly for series and sums, we get that then, therefore, when I multiply this times x sub I minus 1, and this by the same thing, then this inequality still holds, and then I can still put sums over here. And that is exactly the statement that we have right here. So as we take the norms of these partitions to go towards 0, the sum on the left-hand side gets arbitrarily close to the integral of f, while the integral on the right-hand side gets arbitrarily close to the integral of g. And that gives us exactly what we're looking for there. A corollary of this is that, well, if you have a function that is non-negative, then you can just see that we're comparing two functions that are integrable. We know that 0 is integrable as it is a constant function. And so if f of x is greater than or equal to 0, then the integral of f of x is going to be greater than or equal to the integral of 0 going from a to b. But we know that that integral is going to be 0. So that's a neat little corollary there. All right, so this gives us a little bit of an introduction here toward how we can actually rigorously work through integration. We've given a definition of integrals, shown all of the different ways that it can operate, and also given how we can apply different laws and principles with these integrals. Again, our goal here is to try and show that the fundamental theorem of calculus is something that actually works, something so fundamental that we often use it without even thinking about it. But that will do it for me today. Thank you so much. Have a wonderful day.